Hello, welcome to Quantum Leap. Today we are going to discuss very important topic, that is Lagrange's differential equation, Lagrangian polynomial. So this is our Lagrangian differential equation. Here n is a real number, but most applications only integral values of n are needed. Equation number one, this equation number one can also written as like this. Okay, d by dx into 1 minus x square d by dx into n into n plus 1 into y equal to 0. A general solution of this Lagrangian's equation. So the equation number one can solve in a series of ascending order or descending power of x. The solution in descending powers of x is more important than the one in ascending power of x. Let us assume that the solution of equation number one is y equal to summation r equal to 0 to infinity a r x power k minus r. So we need to substitute this y value here. Okay. Y value here first. And then substitute with respect to derivative with respect to x equation number 2. Then you will get dy by dx value. Then substitute that value here. Then again differentiate with respect to y equation number 3, you will get a d square y by dx square, then substitute that value here. Okay. Okay. So if you substitute equation number 2, 3, 4 in equation number 1, you will get this equation. Then go through these simple steps. Then you will get final equation number 5 equation. This one. Equation number 5. This equation you will get. So if you observe here, what I written here already. So x power k minus r minus 2 coefficient term is there, and x power k minus r term is there. Okay. So in this equation number 5, I'm going to compare x power k terms, x power k minus 1 term, x power k minus r minus 2 term. For that, first I'm going to uh, compare x power k. If you suppose if you put r is equal to 0 in this equation, you will get x power k term, only x power k term. Suppose if you put here r is equal to 0, here we will get x power k minus 2. So I want only x power k coefficients only, right? So this is our x power k coefficient. You use r is equal to 1. So like that, we need to uh, solve this equation. So if you use r is equal to 0 in equation number 5, you will get this x power k coefficient terms. This is our x power k coefficient. X power k coefficient terms. Okay. So if you simplify this one, go to the simple steps, then finally you will get this equation. Okay, n minus k into n plus k plus 1 into a naught equal to 0. Here a naught is equal to 0 because if a naught equal to 0, this entire equation solution going to be 0, then there is no chance to solve the a polynomial equation. So if a naught is not equal to 0, then we have two cases. One is n equal to k, case 1, this one. Another one is n equal to minus k plus 1 or k equal to minus n plus 1. So as we discussed earlier, we need to find x power k coefficient, x power k minus 1. This is our next, next coefficient, next x power k coefficient. So x power k coefficient, this one. So put r equal to 1 equation number 5, then you will get this equation, x power k minus 1 coefficient. If you carefully solve this equation by using these simple steps, then you will get this equation finally. This is our final equation. Okay. From this equation, n plus k into n minus k plus 1 is not equal to 0. Okay, because it is already there in first equation, right? N is equal to k, n is equal to k solution, right? So we are already using this equation. For therefore, here a1 equal to 0. Here a1 equal to, then I need to substitute r equal to r plus 2 in equation number 5. Then you will get the x power k minus r minus 2. This is our x power k minus r minus 2 coefficient term. Again, I simplify this equation. I got x power k minus r coefficient term, this one. Okay. If you want to go clearly, let's go one more time here. This is our seventh equation. So if you solve this seventh equation, then you will get this final equation. Okay, equation number 8. So why I am using here the two equation number? This is equation number 1. So if you observe here carefully, denominator value is there. Denominator value. This denominator value slightly modified here. So if you look carefully here, this is modified denominator value. So if you look at this denominator, is these two are same, but for our convenience, I want to use this solution because simplification is going to very easy. We use these terms in Go, these terms also, but you need to take a lot of time to calculate uh, A1, A2, A3, A4, A5 values. So we already know two cases are there. One is n equal to, another one is k is equal to minus n plus 1. So first case, here we are going to use the first case. This is our first case, right? So if I take first case k equal to n, then replace wherever k is there in our final equation. In place of k, I replace n only. Then I'll got this equation. Again, I modified this denominator value like this. So this is our denominator value. Then I modify like this. Okay, this is our modified denominator value. So finally, I got this equation here. a r plus 2 is equal to n minus r into n minus r minus 1 divided by minus 2n minus r minus 1 into r plus 2 into ar. This is our the nth term. Now the polynomial, that is the nth term. Suppose if you use r is equal to 0, 2, 4, 6, then you will get the some values, right? If you use r is equal to 0, you will get a2 value here. Then if you use r equal to 2 value here, then a4, a6, a8 value will get, right? So simply if you solve these equations, see here what I got. So if I substitute r is equal to 0 in this equation, then I got a2 value, a4 value, a6 value. Then put r equal to 3, sorry, r is equal to 1, 3, 5 values in our final equation. This is our final equation, right? Then you will get this equation. This is our equation I got after substituting r is equal to 1, 3, 5 values. First I substitute r is equal to 1. If you substitute r equal to 1, you will get 1 plus 2 equal to 3. Here I got a1 because we already discussed this a1 value equal to 0. If you use a1 value 0 equal to, then you will get a3 equal to 0. So from this information, I'm going to use a1 equal to 0, a2 is equal, sorry, a3 equal to 0, a5 is equal to 0, a7 equal to 0. Our equation number 9. So this is our solution, right? Assumption solution. If you expand this solution, you will get a not x power k plus a1 x power k minus 1. Suppose r is equal to 0 to infinity. Up to you can expand some 6 or 7 terms. So substitute a1, a2, a3, a4 values here. We already know a0 value, a1 value we already know. Okay, a1 value 0, right? This is a2 value, a3 value 0, a4 value, a5 value 0, a6 value. So if you substitute all this a1, a2, a3 value, then common a0 value, then you will get equation number 10. This is our first kind of Lagrangian polynomial. Here the a0 is arbitrary constant and n is the positive integer number. So this is our a0, 3, 5, and so on to n minus 1 into n factorial. So y equal to this a0 value, and this is our uh, Lagrangian first kind equation. This is called first kind of Lagrangian equations. This series is terminating series, and for different values of n, we'll get the different polynomial values. So this is a specially kind of Lagrangian polynomial first kind, which is denoted by Pn of x. Pn of x. So, so if you remember these formulas, this is very important formula for CSIR NET guidance just examination, even or jam exam also. Okay. Then second case. If you use this second case, what is that second case? K equal to n, sorry, minus n plus 1, right? So use this k equal to n minus, wherever k is there, just replace this minus n plus 1 in our 8 prime equation. After replacing this our k, right? Place of k, replace minus n plus 1. So after replacing here also, I modified this denominator. This is our original denominator value. So I modified this denominator value like this for simplification purpose. So like that, if you solve this equation similar kind, So you will get the nth term here also. Okay, second case also. Again, if you substitute this r is equal to 0, 1, 2, 3, 4, you will get this equation r is equal to 0. Substitute here r is equal to 0, you will get a2, and if you substitute r is equal to, you will get a4, similarly a6. Okay, we already know this a1, a2, a3, a5 value already know, right? That is 0, no need to calculate again. Then again substitute this a1, a2, a3, a4, a5 values here. Substitute a1, a2, a3, a4, a5 values, extend this solution. Then replace this in place of k equal to minus n plus 1. So if after substituting, then you will get this equation. This is our second kind Lagrangian polynomial equation. This is here a naught is quite different from the what we saw in earlier Pn of x is Qn of x. It is denoted by the Qn of x. Here a naught is a n factorial divided by 135 in and so on equal to Tn minus 1. So finally, this is these two equations, whatever Pn of x, Qn of x is there, we need to combine these two equations, then you will get this polynomial equation, our Lagrangian polynomial solution. So simply we can write y is equal to a Pn of x plus b Qn of x. So this is our Lagrangian function of second kind. This is our Lagrangian function of second kind. This is the Lagrangian function of first kind. So this is our Lagrangian polynomial solution. If you like this video, please share and subscribe. Thank you for watching.